In the last few classes, we have discussed adiabatic frictionless flow in duct with varying cross sectional area, and as we have discussed, they are simplified flow representing flow in nozzle, ducts, wind tunnels and many such. In our next example of flow through ducts, we will consider adiabatic flow with friction adiabatic flow in ducts with friction and we will assume uniform area, uniform cross section. Now, flow in duct with friction is important in many practical application, as an example in stationary power plants, in aircraft propulsion, high vacuum technology, chemical process plant and natural gas transport through long pipes. We will consider that the wall friction is the chief factor, wall friction is the chief factor and no attempt made to transfer heat to or from the flow. If the ducts are reasonably short, the flow is approximately adiabatic, but if the ducts are very long, then sufficient area is available for heat transfer to make the flow non-adiabatic. However, in that situation the flow can be treated as approximately isothermal. So, you can say that if the ducts are short ducts, the flow are adiabatic, long ducts heat transfer is possible, there is enough area to heat transfer take place and it is approximately, the flow is then approximately isothermal. Once again, we will assume the flow to be one dimensional, that is at any cross section we are considering about the average flow velocity. Then the governing equation, assuming 1D flow, since no heat is added and there are no other type of heat dissipation, the energy equation remain unchanged, which is H plus half U square. So, and which we denote as the total enthalpy H naught. The mass flow rate is again a constant this being the mass flow rate per unit area, and let us denote this by G. Now, substituting this here, what we get is that is, if we combine the two, H 0 minus H square by 2 rho. That is, the enthalpy is now expressed as a function of density alone, H 0 and G being constant. Now, this can be plotted in the specific volume. For fixed H 0, we have different curves for different value of G. And this is the direction of decreasing G. Meaning that this curve corresponds to a smaller value of G compared to these and this. So, this is for a say larger G, this curve represents a larger value of G, and this is a smaller G. Now, if we plot the isentropes, that is lines of constant entropy, so these are all the isentropes. Lines of constant entropy. So, all possible states of the fluid for a given adiabatic constant area flow lie on one of these lines. Now, since we know that for a pure substance, entropy or any flow property is a function of any other two state property. So, for a pure substance, so H so the curves may be transferred to HS diagram. And since all possible states of the fluid for a given adiabatic uniform area flow lie in one of these curves, that is either in the H rho diagram or in the HS diagram, then each of these diagram represents a particular flow, and these curves are called phenocurves or phenolines. So, the curves representing flow in HS diagram are called phenocurves or phenolines. And for all substances, these phenocurves have a general shape which are like this. As before, this represents a smaller g and this represents a larger g. So, these are the general shape of phenocurves for all substances or for all fluids. Now, see that in an adiabatic flow, the entropy cannot decrease, and as a consequence, considering any phenocurve, let us say this, the flow can be either follow this part of the path along this direction or along this. The flow cannot be in this direction or in this direction, that is not possible. This represents, say, the maximum entropy point. Consequently, this upper branch of the phenocurve, in which we see that the enthalpy continuously falls while entropy increases, this represents a subsonic flow. So, the upper branch represents upper branch, in which this represents a subsonic flow, flow where H decreases, S increases. S of course will increase always, and similarly the lower branch that is this part or this part, this is the lower branch and this is the upper branch. This lower branch now represents supersonic flow, where the enthalpy increases and entropy also increases. So, both H and S increase. That is a supersonic flow through a uniform area duct with friction, both H and S increases. And the maximum entropy point represents sonic point. Sonic point, that is both the subsonic flow and supersonic flow, they approach to the sonic point or the point at which the entropy is maximum. So, what we see that a subsonic flow accelerates to sonic condition and a supersonic flow decelerates to sonic condition. So, the effect of friction in a uniform duct when the flow is adiabatic is to accelerate a subsonic flow to the sonic condition and decelerate a supersonic flow to the sonic condition. So, subsonic flow accelerates to sonic condition and supersonic flow decelerates to sonic. Or in other way, the effect of friction is to accelerate subsonic flow with decrease in enthalpy and supersonic friction decelerates supersonic flow to sonic condition with increase in enthalpy. What happened to the pressure? To see what happened to the pressure, we can consider a particular flow with fixed G. Let us say in a duct the flow is at condition A. The flow is at condition A. Then the pressure at this point can be obtained from the constant pressure line passing through that point. Let us say this is the constant pressure line passing through that point. So, this point represents constant pressure line through A, and this represents a pressure of P A. The corresponding point on the total enthalpy line, that is this H0 line. Similarly, here also you can have a constant pressure line. So, this represents P0 A. Now, since the flow can move only along this path, so at a downstream station in the duct, if the initial state is A, the subsequent point will be say somewhere here, and this will of course be a lower value of pressure. So, in this case pressure decreases. This is also of course obvious from other facts that for the subsonic flow the enthalpy is decreasing, because the flow is accelerating. So, the energy of the flow is being converted to kinetic energy part, consequently the internal energy is decreasing, which results in a decrease in enthalpy and pressure. And obviously, the opposite happens in case of a supersonic flow. If we consider again a corresponding point here, this is a curve for P B and this is the point B, and this is of course P 0 A equal to P 0 B. So, in supersonic flow, the flow is decelerating, consequently the kinetic energy is being converted to internal energy. So, enthalpy and pressure increases. So, H and P increases. And since in this adiabatic flow the entropy cannot decrease, so the flow cannot flow from this side cannot come to this side, and flow from this side also cannot go to that side. Consequently, a subsonic flow cannot accelerate to supersonic flow. Similarly, a supersonic flow cannot decelerate to a subsonic flow. So, subsonic flow will not become supersonic, and supersonic flow will not become subsonic. Unless some discontinuity is provided. Unless some discontinuity is present. Now, the limiting pressure, coming back here, the limiting pressure beyond which entropy would suffer a decrease occurs at Mach number unity, and the pressure is again denoted by P star. However, this must be remembered that this P star is not the same P star as in isentropic flow. The value of P star that we derived earlier is not this P star. So, that also this P star corresponding to m equal to 1 is not the same P star found for isentropic flow. Now, also remember that the isentropic relations are also not applicable in this case, because this flow is not isentropic. However, before, as we have discussed, that a stagnation pressure or stagnation temperature can be defined at any point, assuming that the flow there is brought to rest isentropically. So, we can define a isentropic stagnation pressure at each and every point in this flow also, and we will see that this isentropic stagnation pressure decreases as a result of friction, and it decreases irrespective of whether the flow is subsonic or whether the flow is supersonic. So, P 0 defined at each point decreases in both subsonic and supersonic and supersonic flow when friction is present. Now, since we see that the flow here also reaches to the sonic condition if of course, the required length is present or the required amount of frictional force is there, and so a choking occurs due to friction also. So, there is a choking due to friction. Now, let us consider that stagnation enthalpy, flow per unit area and length of duct are such that the Mach number unit is reached at the end of duct. Now, if the duct length is further increased, what we have discussed earlier, from that we can say that no further increase in Mach number if the flow were earlier subsonic is possible. Similarly, if the flow were earlier supersonic, no further decrease in Mach number is possible. So, some sort of adjustment in the flow is necessary. If the flow were subsonic, then the adjustment will be in the form of reduction in the flow rate, that is the flow rate will decrease, and we can say that the earlier the flow was choked. If the flow is supersonic, then this adjustment will involve appearance of shock waves, and for sufficiently lower increase in duct length, there will be a wave propagation mechanism and ultimately the flow is choked. So, if we have a appropriate length, so for a given stagnation enthalpy and flow rate and the length of the duct, if the Mach number of unity is reached at the end of the duct, then with further increase in the duct length, the mass flow rate will fall, and again the maximum Mach number will shift to the tip, to the end. So, we can say that when Mach number unit is reached, that will always reach at the end of the tube, and that corresponds to the maximum flow rate for the given total enthalpy and length of duct, and the flow is choked. So, m equal to 1 can be reached at the end of duct for a given H naught and m dot by A g. The flow is then choked. That is, the mass flow rate is maximum. Maximum mass flow rate is maximum, that is possible for the given condition, and as you have seen that if we increase the duct, then there will be adjustment and mass flow rate will decrease if the flow is subsonic. If the flow is supersonic, a shock will appear and again a mass flow rate will decrease. Now, let us come to the full mathematical analysis for this problem. Let us consider a uniform area duct Let us consider a control volume and these are the control surfaces. Let us say the flow that enters here has flow velocity u, Mach number m, the pressure is P, temperature is T, and so on. And the flow that comes out here has a pressure P plus dP, a temperature T plus dt, flow velocity u plus du, Mach number is also m plus dm, density is rho plus d rho, and so on. Let us say that is the direction of the frictional force, and let us consider this length to be dx. Now, writing the appropriate relations for this, we have from equation of state P equal to rho at t, or in the differential form we have dP by P equal to d rho by rho plus dt by t. We defined speed of sound t, or m square equal to u square by gamma r t, which gives us d m square by m square equal to d u square by u square minus dt by t. So, write equation of state definition of Mach number, you can write the energy equation in the form, since you are considering a perfect gas, Cp dt plus d of u square by 2 that equal to 0, and this results in dt by t plus gamma minus 1 by 2 m square definition of Mach number that is used to obtain this relation. The conservation of mass or continuity equation gives us constant, or which in the differential form becomes d rho by rho plus half d u square by u square equal to 0. So, we already have 4 equations. Now, we will write the momentum conservation. Momentum equation, but this time momentum equation with friction. It gives that the rho a u g u equal to minus a d p minus tau w. Now, this shear stress that acts over all the entire circumferential area. So, this is will be multiplied by area, but not by the cross sectional area, rather the surface area. So, meaning that A is cross sectional area associated with mass flow, and A w is the wall surface area or more commonly known as weighted area over which tau w acts. For a duct flow, a more useful form of this frictional force is expressed in terms of coefficient of friction. So, we define a coefficient of friction, friction F equal to tau w by half rho u square. It is also convenient to write a hydraulic diameter let us say d equal to 4 times cross sectional area by weighted perimeter. And as can easily be seen that if the duct is circular, hydraulic diameter same as the geometric diameter. However, for a non-circular tube, the hydraulic diameter is more useful, and mathematically that can be written as 4 times the area, cross sectional area by weighted parameter, which is dAw dx. And for our use you can write is to be 4 a by dAw dx. Now, introducing this frictional coefficient of friction and hydraulic diameter and also the continuity equation into the momentum equation. So, introducing F d and continuity equation into the momentum equation, get in the differential form minus dP minus 4 f rho u square by 2 or dP by P plus gamma m square by 2 4 f dx by d. So, we get this is our fifth equation. Also additional equation we can use. So, this is our, let us say this will denote as our fifth equation, and coming back, while this is our equation number 1, equation number 1, this is equation 2, this is equation 3 and this is 4. Using definition of P0, that is P0 equal to P into 1 plus gamma minus 1 by 2 m square by gamma minus 1. We have dP0 by P0 equal to dP by P plus gamma m square by 2 plus 1 by gamma minus 1 by 2 m square which will be our equation 6. In many cases an impulse function is used, and which is a very useful, particularly turbomachineries and propulsion devices, and which can be defined as P A plus rho A U square. And turbo machinery applications. And this results in dF by F equal to dP by P plus gamma m square by 1 plus gamma m square dm square by m square, and this will denote as our seventh equation. So, you see that we have now 7 equations in 7 unknowns, and instead of treating them as differential equation, we can even treat them as algebraic equations, or then the unknowns are the differentials. So, we have here 7 equations with 8 differential variables. So, we have 7 equations with 8 differential variables. The 8 differential variables are d rho by rho, dP by P, dt by T, d u square by u square, dm square by m square, dp0 by p0, df by f, and dx by d. So, what we have all these 7 equations, we treat them as algebraic equation, not as differential equations, and treat these as the variables. So, we have 7 equation for 8 unknown variables, and we can express 7 in terms of the 8th. So, we express 7 in terms of the 8th. Now, for 8th we can have any one as our choice. However, physically this flow is the driving mechanism in this flow is the friction, and hence the term representing viscous friction can be taken as the independent. So, physical consideration, that is driving mechanism being the friction force being driving mechanism, we can see that for f dx by d can be chosen as the independent. This is also justified because this contains the geometric parameter dx by d and obviously more independent than the others. So, we will now solve these 7 equations for the 7 unknown variable. Of course, all these variables will be expressed in terms of 4 f dx by d, and we will do that in the next class.